Hello, today we're going to talk about the different types of systems of equations. And as you can see by our nifty little picture here, there's actually three possibilities that we could have occur. One possibility is that our system is what we call inconsistent, and that essentially means that there's no solution that is going to satisfy our system of equations. So a solution we usually think of as an x and y coordinate, and there isn't a solution because our lines are actually parallel. They'll never actually cross and have any point or x, y value in common. The second case we're going to look at is what we call a consistent independent system. And we'll talk a little bit more about the nameage here, but consistent means that there is one or more solutions. Independent is just referring to the fact that our two lines don't necessarily depend upon each other to maintain this one solution case. So the consistent independent case is when we do have a singular solution. There's a particular point that satisfies both of our equations, and that would be our intersecting point of the two lines. So if the lines do in fact intersect, we would say it has that one point, whatever that xy is, as the solution, and we classify it as that consistent independent system of equations. And the last possibility is we have a consistent dependent system of equations. And that is occurring because essentially you have the same line twice. It would be a line kind of graphing on top of itself. And there we actually have not none or one, but an infinite number of possible solutions. And all those solutions would be all the different points occurring on my line. So we would say it is a consistent system because it does have one or more solutions. However, this time we say it's dependent because if I change any aspect of my system of equations a little bit, like change one coefficient, on my x or the y, or any aspects of our equations, that it completely changes the situation. That now I would either have parallel or potentially intersecting lines. So we say it's dependent because any one little change in our system is going to affect what's occurring, and our other equation would have to change the same way to maintain this same line graphing twice. So one thing I want to talk about in this video is how we write our solutions for these three different cases, because in some instances the solution may be pretty straightforward, and there's also instances where it's not. So let's talk about what the solutions, what our answers would look like for each of these cases. So the first case was the inconsistent independent system. So inconsistent is referring to the fact that there is no solution, right? We would have parallel running lines that never cross and would never share any xy points. So how would I see that? I mean, if I graph the lines, I can tell that they're parallel, but graphing is not always the best way to go because our graphs can be inexact. We may have lines that actually have very similar slopes and they look like they're parallel, but in fact they do eventually intersect and have a solution. So a far more reliable way of determining if there is a solution is to use either substitution or elimination. On this particular problem, I decided to use substitution because this first equation, 2x minus y, was just very conveniently set up to easily solve for y. So I solved that first equation for y, and then I substituted or replaced y in my second equation with what I knew it was equivalent to in the first. So in the first equation, on the top equation, y is equal to 2x minus 5, and then I replaced that 2x minus 5 into my second equation. And how we're going to know we have this no solution case happening is as we go through this solving process. Normally we would solve for x equals, right, in this particular instance. But what ends up happening is my x values, in a sense, add to 0 or cancel themselves out. And the resulting equation that I get is negative 10 equals negative 6. It's a false equality. And anytime that happens, when your variables naturally add out or add to 0 or cancel out and you have a false statement remaining, that's an indicator that it's a no solution. So how would I write my answer? I would say no solution. The other possibility is I could write my solution as an empty set. So the notation for the empty set is the circle with a line through it. Or you could literally write a set with nothing in it. So your curly brackets to indicate a set with nothing inside the set. The second possible type of system is our consistent independent. and that's the one that has a single solution, a single point where my two lines is crossing. So if I did this graphically, I would look at where that XY point is. Now, one issue again with graphing is it could be inexact unless my XY coordinate happens to be right on a whole number, a recorded tick mark on my X and Y axis. I don't really know where that point is, right? So just as a for instance, say I was in between, actually this is a great example, I'm between 0 and 1 on my x-axis, and this graph doesn't perfectly mirror our solution, but I also wouldn't exactly know where I am on y. So there is some times where graphing is not going to be an appropriate way to solve these systems. This would be definitely a case where we want to do an algebraic solution. This particular equation I solved by elimination because I very conveniently and nicely had a negative y and a positive y. So I could add my two equations using that elimination method and easily eliminate the y. So that's why I went this elimination route on this one. And so I eliminated y and I got 5x equals 1, so my x value is 1/5. And then we still need to substitute. Once we find one variable, you still have to substitute that value to find our other variable. So you could plug it into either equation. I put it into the bottom equation and solved, and I got a value of y, which is -23/5. And so here, that would be the x and y coordinate. So we could write it as x equals 1/5 and y equals 23/5. Usually, though, because we are connecting these back to graphs, we write it as an xy coordinate in the point form. And our last type of solution, consistent dependent, that's the one where you would have a line essentially graphing twice right on top of itself. That one actually does have a pretty tricky way of showing or writing out the solutions. So we definitely want to take a look at that. And really the key thing there, we do need to do some algebra work to write that solution. So graphically, that one may be a little bit easier to identify on the graph. You would essentially be graphing the same line twice. If we decided to solve this algebraically, either using substitution or elimination, in this instance it looks like I went the substitution route again. I took my top equation and solved for y, and then plugged y into the secondary equation. And we have a similar thing happen to what we saw for the case of no solution. The values of x are adding to 0, but the resulting equation, instead of being false, is actually true. 15 will in fact always equal 15. So when your variables cancel out or add to 0 and you get a true equality, that's indicating that we have this consistent dependent system occurring. So how do I write that? Well, although I do have an infinite number of solutions, that's not describing all the different points that are on my line. I need to be able to describe if I have a particular x value known or a particular y value known, figuring out what the other coordinate would be on my graph for a point on my line. So there's two ways that we could go about writing our solution. It's going to be a solution set. So here are kind of the two different ways I could write my answer. So it's going to be a set of xy coordinates such that, and then here we kind of get some freedom. I could either let x be the number that can kind of freely change. So x could be any real number, and then I just need to write the relationship in terms of x for my value y, right? So the idea is if I said, say x was 1, then I could easily calculate y by plugging in an x value of 1. That's what this second condition is finding the value of y. And where I got that equation was actually from the substitution process earlier. I had solved for y and got that it was 2x minus 5. I just took that same equation and wrote it in because it's telling me, it's describing how we would find y, right? You would take your value of x, multiply it by 2, and then subtract 5. So that's one possible way of writing our solution set of points. The other option is to let y be that value that can take on any real number. So if I let y be the value that can take on any real number, then I have to write an equation to determine what x would be for that particular y. So there, if we decide to go that route, we'd have to take one of our equations and essentially solve for the x variable. So I took the original equation 2x minus y equals 5, and I solved for x. And when I solved for x, I got that it was the y value added with 5, and then all divided by 2. So again, the idea would be, now if I plugged in a value for y, say if I let y be 1, I could easily plug in a 1 for the y value in my equation and figure out what x would be, right? X would be 1 plus 5 is 6 over 2 is 3. So I could easily determine one of those many infinite points that are on the line. And that's it. So the key things we want to remember or take away from these 3 systems of equations, we definitely want to know of the 3 possibilities. So I want to know that I could have no solution or an empty set for my answer. I could have one solution or a single xy point as my solution, or I could have any point on my line. I could have an infinite number of solutions of those points, and we would describe our solution as a coordinate xy on this line. So we would describe the set of points on this line. And then you may be asked to, for the type of system, just kind of remember the 3 cases are no solution is that consistent independent system, one solution is consistent dependent, and infinite solutions, all the points on the line would be consistent dependent.